Let's look at some of the sapling problems that you have in homework number 3. The first couple of sapling problems are just giving you everyday objects, asking you to classify them as chiral or achiral based on whether or not they are identical to their mirror image. On question 3, it's giving you Lewis structures or partially condensed structures of molecules and asking you to find the chirality centers in these molecules. And they may have multiple chirality centers and they may have no chirality centers at all. So let's just kind of review how we're going to go about finding chirality centers. When we look at a carbon atom, if it has 3 hydrogens on it, it is not a chirality center. Remember, a chirality center is a carbon atom that has 4 single bonds to 4 unique things. So if you have 3 hydrogens, then that's not going to be a chirality center. Or if you have 2 hydrogens, also not a chirality center, 2 of the same thing. 2 hydrogens, 2 hydrogens, 2 hydrogens, 3 hydrogens, all of these are not chirality centers. Carbon number 9, 3 hydrogens. Carbon number 8, 2 hydrogens. We're left with maybe carbon number 4. It might be a chirality center, it might not. We have to analyze exactly what's attached to it. Carbon number 4 has a CH3. It also has a CH2CH3, so those are 2 different things. It has a CH2CH2CH3 and a CH2CH2CH3. So that means that because these 2 things are the same, it also is not a chirality center. So this molecule is not going to have any at all. Let's try again with compound number 2. Carbon number 1 has 2 hydrogens on it, so not chirality center. Carbon number 2 has 2 CH3s, one on top and one on bottom. Those are 2 identical things, so it's also not a chirality center. Carbon number 3 might be. Let's have a look at what we've got going on there. Carbon number 3 has a bromine. It has a hydrogen. It has a CH3. And then it has this, which is different. So carbon number 3, yes, that is a chirality center. Let's look at carbon number 4. It's a CH3, so it has got 3 hydrogens, not a chirality center. So use that strategy for this question. Question number 4 is very similar. It's just asking you to analyze each of the carbons that it's pointing at. And if you think that the carbon is a chirality center, you're just going to drag one of these little stars. And that's wrong because that carbon has 3 hydrogens on it. It's not a chirality center. But that's how you're going to mark a carbon that you think is a chirality center. Question number 5 is exactly the same. And question number 6... also the same thing, but this one is actually kind of tricky. So I want to go over some of the trickier ones on this particular problem with you. So what we're going to look at, what I really want to start with is, we'll just do all of them because it's not asking us to do every single carbon in every molecule. So first of all, remember if a carbon is part of a double bond, it cannot be a chirality center. So let's black those ones out, not an option. Double bond carbons cannot be chirality centers. Let's get rid of them. And I'm looking for easy things to eliminate. On molecule number C, there's a CH3 carbon, so let's get rid of that. That's definitely not a chirality center. I think I've got rid of all the easy stuff. So let's go back to molecule A and the one that I skipped, this carbon right here. We need to see if it has 4 different things attached. It has an OH, that's one thing. It has a hydrogen, that's a second thing. And then it's got this, it's part of this ring. And so when a carbon is part of a ring and we're trying to determine if it's a chirality center or not, what we're going to do is walk around the ring in both directions to see if the path is the same when we move to the left or we move to the right. So let me do this with you. When we move to the left, the first thing we come to is a CH2. When we move to the right, the first thing we come to is a CH2. So far the path is identical. Let's go back to the left-hand path. In our next step, we've got another CH2. In our right-hand step, the next thing that we come to is an alkene, which is different. So at this point in the path, the left-hand path and the right-hand path are no longer the same, which means that this part of the molecule is different from this part of the molecule. I've really marked that up a lot. This, that carbon is chiral, because the path to the left is not the same as the path to the right. Let's practice that with the molecule B right underneath it. So we're being asked to look at this carbon. We have a hydrogen and we have a CH3, so those are two things. And again, we're in a ring, so we're gonna walk to the left and to the right around the ring to see if the path is the same in both directions. So when we go to the left, the first thing we come to is a CH2, and to the right, the first thing that we come to is also a CH2, so that's the same. In our next step, we come to a carbon that's part of a double bond. If we're going to the right, the next thing that we come to is also part of a double bond. And once our left-hand path meets our right-hand path, if the path to the left and to the right have been identical, that means the molecule itself is identical. That those two paths are identical. The left-hand side is identical to the right-hand side, and that means that this is not a chirality center. That's a no. So let's move to molecule C. We've got 3 carbons in rings, so we're going to be able to get a lot of practice. This carbon, the first one we're going to look at, it has this CH2CH3, so that's one thing. It also has a hydrogen, so that's something different. That's number 2. And then we've got a path to the left and a path to the right. And we're going to walk to the left and walk to the right and see if we can see if we're taking the same path or a different path. So the first thing to the left that we come to is a CH2. And when we're going to the right, that is not a CH2. It's part of the ring, but it's got this thing attached to it, which makes it different. These 2 carbons are different. Therefore, the left-hand path is different from the right-hand path, and yes, that particular carbon is chiral. Let's try this guy right here, see what we get. So this guy has this ketone thing attached to it. It also has a hydrogen attached to it, and because it's part of the ring, we're going to walk to the left, we're going to walk to the right, and see what we get. When we walk to the left, we come to a carbon that has a CH2CH3. When we walk to the right, we come to a carbon that has something other than a CH2CH3. The left-hand path and the right-hand path are not the same. Because the left and the right path are not the same, this carbon, yes, is chiral. Let's practice another one. This carbon has ketone. It has a hydrogen, it has a path down and a path up, and we're going to compare the path down to the path up. If we go down, the first thing we come to is a CH2. If we go up, the first thing that we come to is a CH, something big is attached. The path up is different from the path down. That carbon is chiral. So hopefully that helps you out with that. You actually have a couple problems like that, I think. Oh no, I guess maybe that's the only one. Question number 7 is like question, I think, number 3 that I already walked through with you. Here's one. Oh, this is beautiful. This is giving you 2 different molecules, and it's asking you if they have a relationship. Are they enantiomers? Are they constitutional isomers? Are they the exact same compound? And the easiest way for you to do this, I'm going to say, first of all, is to take this molecule and redraw it so that it is on its side, matching this particular molecule right here, just in terms of being on its side. And you want to be really careful when you redraw it on your side. Be careful that you don't move around any of the things that are attached to the molecule. So I'm just going to rotate it. I literally just rotated my iPad, even though that does not do you any good. So I'm rotating this molecule onto its side, Notice that I'm not making any changes to wedge or dash. I'm not trying to draw this molecule as an enantiomer or anything. I'm just trying to copy the molecule without changing anything. I'm being really careful that I don't want to lose any kind of carbons. I don't want to mess anything up. So I've redrawn the molecule on its side. That's going to make it easier for me to compare the two molecules. So I'm comparing this molecule to this molecule. And you're going to be asking yourself questions like, are they exactly the same? Constitutional isomers would mean that they have the same formula, but they have different connection of atoms. So the atoms are put together in a different order. Enantiomer would mean that they have the same connection, but they are mirror images. So analyze those two structures and see, maybe they're the same. So that would be totally identical. And then not isomer would just sort of be your none of the above option. Question number 9 is asking you to draw the enantiomer of each molecule. And if it doesn't have an enantiomer, then just redraw the molecule exactly the same. Looking at the first one that they give us, that carbon that's in the middle of the molecule, notice that it has 3 CH3s. So it's not chiral because it has 3 of the exact same things on that carbon, which means it won't have an enantiomer. If a molecule is achiral, it won't have an enantiomer. So that's not very exciting. I'm not going to do that one. But let's do the second one. Let me do the second one for you. So for this, we're going to draw the enantiomer, and we have 2 options of how we draw enantiomers. Remember that you can choose when you're drawing them, you can choose to either totally draw the molecule as a total mirror image, which maybe that's actually what I'm going to do. I'm going to draw a total mirror image for this. So I am just drawing this molecule completely backwards from the molecule that was provided in the problem. My single bond with the nitrogen. Look at this cool, I don't know if you've found this tool yet when you're drawing. If you go over to the More option, notice how they have this plus H minus H button. This allows you to add hydrogens. So if I'm clicked on plus H and then I just start clicking on the atom where I want to put hydrogens, they just show up. If you get crazy with it and put too many on there, then you just use minus H to get rid of them. It makes it a lot faster. So here's one option for doing this. I've just drawn the absolute mirror image of the molecule. Then remember, you have a second option. So I'm going to do the second option down here. Your second option is to leave the molecule pretty much intact. You're going to draw... Oh, I didn't mean to do that. We're going to draw this molecule without really making any changes to what's on the left, what's on the right. We're going to leave everything in the same spot. But all that I'm going to do is change everywhere that it's a dash, I'm going to turn it into a wedge. And everywhere that it's a wedge, I'm going to turn it into a dash. And this, it really does not like that. Doesn't like me to be in the full screen. So there's your other option. You can use either one, whichever one you're the most comfortable with. And let's see what else we have. Problem 10, same thing, drawing in an enantiomer. Problem 11, the same thing, to draw in an enantiomer. Problem 12, this one's kind of tricky. It wants you to draw an alcohol, 5 carbons, contains a chirality center. So this means you're going to have to get creative. You're going to put together a 5-carbon molecule, like maybe it's a 5-carbon chain. I made 5 carbons there. And you need this molecule to be an alcohol. So that means you need to have an OH on it, like that. And you need to arrange the atoms in this molecule so that there's a chiral carbon somewhere. Now, the way that I just drew it, I have 1, 2, 3, 4, 5 carbons, and I have the alcohol, the OH group, but I don't have any chiral carbons in this molecule. So this isn't going to work. I know that that's not going to be the right answer, but maybe I could try putting that OH somewhere else in the molecule. Like maybe, oh, that's not what I wanted. Maybe I could put the OH right here and see if that makes the molecule chiral. Or try a few different options of where could you put that OH group that would make the molecule have a chiral carbon. And then the last one that I want to look at with you, number 14, it's asking you to identify which pairs of molecules are enantiomers, mirror images of each other. So here we're just looking at the way the molecules are being represented. Remember, there's 2 different ways that we can draw enantiomers. Either they are straight up mirror images, the way that they are represented. So if you imagine, like if there was a mirror right here, are these 2 mirror images of each other? And it sure looks like we've got the SH thing and the CH3 thing. We've got the CH2, CH3 in the back. Like, yes, that definitely looks like they are mirror images of each other. If the other option is that they are drawn with, not being mirror images. Everything on the left is still on the left and everything on the right is still on the right, but they've switched the wedge to the dash and they've switched the dash to the wedge. So when we look at the second example, we can see that they're not being drawn like mirror images. So then our question is, are they switching the wedge for the dash and the dash for the wedge? Let's look at our wedge and dash situation. Well, those are both hydrogens. That carbon's not even chiral. Those wedges and dashes are not being switched. That's like a trick. This is a no. Those are definitely not enantiomers. What do we got with our next one? Are they being drawn as mirror images of each other? It sure looks like mirror images. That looks like that's a yes as well.